Good morning. I'd like to begin by going back and clarifying something. In the first semester, most of your efforts were about doing derivatives and applying them in one way or the other. We would think about the graph of some function f, the graph of y equal f of x, that is. We would select some particular x value, c. The function value, f of c, is of course the y-coordinate on the graph. The first calculus problem that we investigated was if you look only at the part of the graph that is close to the place where x is c, approximately the graph looks like a straight line, the tangent line at that spot. We made up a name for that slope. We called it f prime at c, or dy dx evaluated at x equals c. On a straight line, though, you need typically 2 points in order to get a slope, and I've only specified that x is equal to c here. What you did back in the first semester was this. You imagine that you have some small number delta x, and that you look at the graph of the function at x equals c and also at x equal c plus delta x. The y-coordinate at this new point is function f evaluated at the x-coordinate c plus delta x. Since we have 2 points, I can calculate the slope of that line, which, while not the line that I'm actually after, isn't too different from it if the delta x is small. The slope of that line that we're looking at is how much the y-coordinate changes divided by how much the x-coordinate changes. Sometimes people will call the top of the fraction delta y, so that this is delta y divided by delta x. As stated, though, this isn't the slope of the straight line we're after. If delta x is small, though, this should very closely approximate it. So I can imagine taking the delta x to be very small, and then smaller still. I could think of taking the limit of these fractions as the delta x tends to 0, and I'll declare that to be f prime evaluated at c. I can't emphasize strongly enough, though, when we take that limit, that doesn't mean generically set delta x equal to 0, because if you do that, you'll end up trying to calculate 0 divided by 0, which doesn't tell you anything. Almost immediately, you drop all pretense and start using the letter x instead of the letter c, and take this formula to be the definition of f prime of x. At this stage in Calc 1, they made you work some problems of this nature the hard way. For example, suppose that f of x is x squared plus 3x plus 1. Not to insult your intelligence, but what that means is the way you do f to a number is you square the number, you add in 3 times the number, and then add 1. If I calculate this limit that I'm interested in, firstly, I need to figure out what f evaluated at x plus delta x is. So I'll take x plus delta x, square that, add in 3 times that, and then add 1. I subtract f of x, which is x squared plus 3x plus 1, divide by delta x, and then I look at what happens to those fractions as the delta x becomes very close to 0. There's going to be some algebra involved. The result is fairly horrible looking, but luckily some things will cancel out. I have an x squared term there, and then later on I subtract x squared. Those cancel out. There is a 3x term here. Later I subtract 3x. Those terms cancel out. Lastly, there's a 1 as a term added in, and a minus 1. So those cancel out as well. Even so, I can't just set delta x equal to 0 because I'll still get 0 divided by 0. On the other hand, if you look at the top of that fraction, every term has a factor of at least 1 delta x in it. When we're taking the limit as delta x tends to 0, I'm thinking of numbers for the delta x that are very, very close to 0, but not exactly 0. For all such things, thinking of the fraction only, this delta x is not 0, neither is that one, which means it's all right to cancel them out. This fraction is not always 2x plus delta x plus 3, but it is that number whenever delta x is not 0, which are the ones that we're looking at. In terms of this limit, x is a constant. It's the x value at which I'm trying to find the slope of the tangent line. 3 is an actual honest-to-goodness constant, so I have to ask myself, how do the numbers 2x plus delta x plus 3 act as you allow the delta x to become close to 0? You get results that are close to 2x plus 0 plus 3. This limit exists and is 2x plus 3. Any reasonable person is thinking at this stage that we have a small bag of tricks to calculate derivatives. F prime of x is the derivative of x squared plus the derivative of 3x plus the derivative of 1. Other tricks that we know say that that would be 2 times x plus 3 plus 0, which is 2x plus 3. So why would you go through all of this? The answer is this contains the meaning of these calculations that we're doing. Our bag of tricks to let us quickly differentiate things of this nature and other things are conveniences for us, but the meaning is contained within the limit definition. The reason that I'm bringing this up is, in terms of integration, something exactly similar happens. If I asked you to calculate the integral from 1 to 2 of 3x plus 1 with respect to x, if you'll remember what you did in Chapter 4 of the first semester course, this is easy on one level. I'll find an antiderivative for 3x plus 1. I'll evaluate it at x equals 2, evaluate at x equal 1, and then subtract those two quantities. But just as with the bag of tricks for derivatives, This is a technique used to evaluate these things. It doesn't tell me what the integral is supposed to represent. In our first set of topics, that's going to be our main focus. We're going to look at applications of integration, and it's all going to be based around knowing what the actual definition of the integral from, say, 1 to 2 of 3x plus 1 with respect to x is. To mimic what we've done before, for now, I'm going to suppose that I've got some function f which is continuous and positive on the interval from a to b. Continuous means the graph doesn't act badly. There are no vertical asymptotes or anything like that. Positive means the y-coordinates on the graph of the function are positive, meaning that the graph itself is above the x-axis. The first integration problem that we looked at was this. Calculate the area starting at x equal a, ending at x equal b, above the x-axis, but under the curve y equal f of x. The machinery that we used to do this is kind of involved. We're going to divide the interval from a to b up into a number of smaller intervals. We will chop it up into n of them. x0 will be a, x1 will be an x number larger than x0, x2 will be larger than xa, and so on and so forth, until you get to x number n, which is equal to b. This is called a partition of the interval from a to b. This symbol is pronounced norm of partition delta. It's the largest width of any of these subchunks that we have here. It's the biggest of all xi minus 1, where the I can be anything from 1 up to n. We will call these widths delta x number I. So, for instance, the distance between x1 and x0 would be x1 minus x0. I'll call that delta x number 1. In the second chunk, I'll look at the horizontal distance from x2 to x1. I'll call that width delta x number 2, and so on and so forth. Notice that in general, I don't have to have the same widths all the way across. Sometimes it'll be convenient for me to do that. Having split the range from A to B up into these smaller pieces, I'm going to think about the area associated with each one of these smaller pieces. For instance, I'm going to think about the area associated with that piece. If I can get some reasonable way of thinking about that, I will add up all such things, and I'll have an estimate for the total area under the curve. To make the estimates better, we make the delta x's small. We make the biggest of them tend to 0, which makes all of them tend to 0. We will take the limit as the norm of the partition tends to 0. One of these smaller chunks goes from one of the x numbers to the next one. So this horizontal length is delta x number I. If f is continuous and the delta x number I is small enough, f doesn't have a great deal of wiggle room as to what its function value can be for x's that are within the subchunk. So what people will do is this. I'll select some x number in chunk number I that I'm going to refer to as Ci, and I'm going to say that this is a representative x number for chunk number I. I'm going to approximate the situation by thinking of chunk number I as roughly being a rectangle. It's delta x number I across the bottom, and it's f at Ci in the vertical direction. That is to say, the area of chunk number I is approximately f evaluated Ci times delta x number I. I want to reiterate here, at this stage, delta x number I is an actual number. It might be 2 or 0.7 or 0.1 or something. F of Ci is f evaluated at an x number, since that's the variable in the problem, which is within chunk number I. If I add up all the contributions from the different chunks, the area is approximately the sum, I equal 1 to n, of f evaluated at C number I times delta x number I. Those sums are called Riemann sums. If it's the case that as I allow the norm of the partition to tend to 0, that all of the corresponding Riemann sums tend to a certain particular number, then we will say that the function is integrable on the interval from a to b. It's possible to prove, although we're not going to, that if you have an interval from a to b where the function is continuous, then the function is integrable on that interval. Presuming that this limit exists, this would tell me the area under the curve starting at x equal a, ending at x equal b. I want to reiterate there are some strings attached here. I'm assuming the function is continuous and positive. If either one of those things is not true, you have to be a lot more careful about it. At the moment, though, I'm going to assume that this limit exists. We're going to make up an abbreviation for this. You could pronounce this as the definite integral of f from a to b with respect to x. Or you could rearrange the language a little bit if you like the sound of different ways, like the integral from a to b of f of x with respect to x, or the integral from a to b of f of x dx, although that's beginning to obscure the meaning of this. Anytime I have a limit, as some norm of partition tends to 0, of the sum of some expression that involves one of the values of the independent variable within chunk number I times how big chunk number I is. When I see limit of sum, I'm going to write down an integral sign. Instead of writing delta x number I, I'll write dx at the end. Instead of writing f at Ci, I'll write f of x, and then the only other thing I have to specify is the relevant range of x values, which in this particular situation goes from a to b, which are my limits of integration. To actually calculate integrals using this kind of setup is horrible. It's even worse than doing derivatives from the definition. If I want to think about the integral from 1 to 2 of 2x with respect to x, if we know our antiderivative trick, an antiderivative would be x squared. My integral would be 2 squared minus 1 squared. That would be 3. If I want to think about this in detail in terms of the definition, that's not what I do. I have to do the limit argument instead, which, as we're about to see, turns into a mess. To keep this from getting completely out of control, I'm going to chop the interval from 1 to 2, which has length 1, up into n equally sized subchunks. Each chunk will be 1 over n wide. I'll call that delta x, since there's only going to be one of these delta x's. X equal 1 is equal to x0. X equal to 2 is equal to x number n. X number 0 is 1. X number 1 is delta x more than that, so that'll be 1 plus delta x, 1 plus 1 over n. X number 2 is delta x more than x number 1 was, so that will be 1 plus 1 over n, and then add 1 over n, 1 plus 2 over n. X number 3 is 1 plus 3 over n, and so on and so forth. Hopefully it's pretty clear that x number I is 1 plus I divided by n. Within each subinterval, I have to pick a representative x value, and out of sheer laziness, I'll just pick the right-hand end of the subinterval. While the individual x numbers are indexed 0 through n, there are only n subintervals, which is why I have a 1 here. The terms that I'm going to add up in my Riemann sum looks like f of ci times delta x, which, after you put the values in and do some algebra, turns out to be 2 over n plus 2 over n squared I. I have to add up all such things and then take the limit as the norm of the partition tends to 0. You have to be a little bit careful when you're looking at this sum. I'm going to add up n terms, each one of which has an I value. The I can go from 1 to n, and each one of the things that I'm going to add up look like this. This is an ordinary algebra sum, so I don't feel bad about rearranging it as I like. I have n quantities inside of these brackets, and each one of them has a term 2 over n. So when I add the 2 over n's up, it's going to be 2 over n plus 2 over n plus 2 over n, and so on and so forth. There are n of those. In the other terms, there's a 2 over n squared, which I could think of as 2 over n squared times 1. I'll have a 2 over n squared times 2, 2 over n squared times 3, all the way out to 2 over n squared times n. When I add up all of those things, they all have a factor of 2 over n squared, and then there are factors 1, 2, 3, all the way out to n. It's a known fact, though, that 1 plus 2 plus 3 all the way out to n is equal to n times n plus 1 over 2. I can use that to simplify the expression that we have here. this term is 2. In this term, I can cancel the 2's out. I can also cancel an n out between the numerator and denominator. The second chunk, n plus 1 over n, can be written as n over n plus 1 over n. N over n is 1, 2 plus 1 is 3, plus 1 over n. 1 over n was delta x. So when the dust finally settles, for this choice of partition, for this choice of selection of C numbers, the Riemann sums just work out to be 3 plus delta x. So using the definition, the definite integral from 1 to 2 of 2x with respect to x is 3, which is what we knew we were going to get, but this is the definition. It should be obvious that working with this is even worse than working with the definition of the derivative, so we're going to be clever here. We're going to use this kind of thinking to set up an integral to solve some problem, and then we don't evaluate the integral using the definition. We use our bag of tricks from Calc 1. I want to imagine having a three-dimensional solid shape, sort of parabolic looking. It's 9 units in the up and down direction. It's 3 across the base in terms of the radius, and for any other location within the surface, and for any other location within the solid, the cross-section is a circle. I'll set up my variables this way. X equals 0 will mean that I'm down at the bottom of the figure. X equal 9 will mean that I'm up at the top, and for some other x, I'll have a circular cross-section whose radius is square root of 9 minus x. I just made this up as an example. I want to figure out what the volume of that solid is. I'm going to take the range of variable values, x, which goes from 0 to 9, split it up into a whole bunch of smaller pieces. I'm going to select one of these pieces and think about the region of the solid that corresponds to that piece. I'll enlarge it here. The change in the variable, which in this case is the change in the up and down for that one piece, will be called delta x number I. Within that one piece of x values, we'll need a representative x number that I'll call C number I. According to the setup of the problem, if I know the x number, the radius of the corresponding circle is radical 9 minus that x number. So I can estimate the volume of this one chunk by calculating the area of the circle of the radius radical 9 minus ci, multiplying it by the perpendicular height, delta x number I. Of course, the square of the radical of 9 minus ci is just ci. If I add up all such contributions, then I've got an estimate for the total volume, and then I'll take the limit as the norm of the partition goes to 0. But if you look back to what we said previously, This is the definition of a definite integral. Limit of sum turns into an integral sign. Delta x number I turns into dx, and in what remains, every place where I see the representative x value for chunk number I stop writing ci and I start writing x instead. The only thing that remains is to specify the appropriate range of x values, which for us starts at x equals 0 and ends at x equals 9. So what's happened here is I've looked at a problem that I didn't know how to solve. I carved it up into a bunch of much smaller problems which were easier to think about. I added up the contributions. I take the limit to make my approximations accurate, and in the end, I find out that the thing that I need to figure in order to know the volume of that solid shape is the definite integral from 0 to 9 of 9 minus x with respect to x. What I'm not going to do is to use the definition of the integral, the limit of sum definition, to actually evaluate that integral. We use the definition to set the integral up, and then once we've got it in our hands, we will evaluate it any way we can. This one is easy. This one is easily done using Calculus 1 techniques. This is going to be our general strategy for a while now. We're going to have some problem that we're interested in. We will think about it as the limit of a sum. We can then turn that into an integral and then do the integral however we can. I believe I'll stop there for today. Next time, we will look at a problem that we already know the answer to, but we're going to look at it from a new point of view. Until then, I hope everybody has a good day. I'll talk to you again soon.